first of all, thanks to the organizer for giving us the opportunity to talk about this work. So, I would like to talk about our recent work where we looked into the non-equilibrium characteristics in presence of hydrodynamic interaction. So, from morning we are hearing many talks, and by now it's clear that if we understand the non-equilibrium characteristics of various system, aspects of interactions are very common. It can start from a simple system, let's say a colloidal particle in a harmonic trap. It's connected to bath with two temperature. So that particle is connected, it's interacting with bath with two temperature. Or you can construct interaction to know more about such system. Let's say you have an active particle, you want to know about the activity of the bath. You can put a probe particle there and use that interaction with the bath to know about that. Also, you can learn more about like how non-equilibrium the system is by putting such colloidal probe connected to an active systems and things like that. And oftentimes, to understand the non-equilibrium characteristics of such system, what we consider the whole system with a spring mass like system, where you consider, let's say in the simplest form, you have 2 degrees of freedom. They are coupled via a spring mass type of interaction, and those are at different temperature. And most time we consider the noise sources which are involved in this simple dynamics are mutually uncorrelated. So these type of systems are multipartite. You can consider the noises are not mutually are not correlated. Okay, so for this type of system, we know that if we can measure this type of higher order interaction, we can estimate the dissipation of such system in better form. But for a generic kind of interaction, there can be many kind of interaction. For a generic kind of interaction, what will happen if the strength of the interaction is enhanced? What will happen to the non-equilibrium characteristics? It is generically unknown. Or let's say if you have a system where the noise sources are mutually correlated, giving rise to non-multipartite or co-evolving dynamics. In such situation, the effect of interaction on promoting the non-equilibrium characteristics is typically unknown. So we can think of a simple interaction, that is hydrodynamic interaction, which is nothing but an interaction which couple the dynamics of a 2 colloidal particles which are close by. So if we consider two colloidal particle, microscopic colloidal particle are trapped close to each other, separated by a distance d, the dynamics of these 2 particles are coupled by a hydrodynamic interaction. And these are pretty simple interaction, and people have studied the dynamical effect of this, and it is known that even in equilibrium, the dynamics of these 2 particles are anti-correlated at short time. Also, it is known if you move one of them, you can get a resonance like behavior in other, you can get synchronization also. Okay, and also there are some works with multiple such particles, some works also told from Professor Yale's group, and many other observations are done with the hydrodynamic interaction. And simply if you consider just 2 particles connected by hydrodynamic interaction, you can write coupled Langevin dynamics for it. Interestingly, here the deterministic force as well as the stochastic force both are coupled via a hydrodynamic interaction tensor, and which consists of this epsilon, which is the coupling term, which depends on the size of the particle as well as the distance between them, and the noise involved are cross correlated like that. Now in recent times, and this cross correlation is giving to a non-multipartite interaction, and in recent times people have started to looking into the non-equilibrium characteristic in such system, and people like Beru et al, they have looked at like how much heat flow from one particle to another due to such interaction, and they do it like considering trajectory based energetics to individual particle, and they got some apparent violation of LRG balance and things like that. Then there are other works even from Reisman's group people have looked into some other idea how to characterize the irreversibility in terms of phase space, current area and closing rate. So what we wanted to understand is that let's say we have a system with hydrodynamic interaction and non-equilibrium setup is going on, how the interaction changes the non-equilibrium characteristics in terms of total entropy production rate, and whether we can tune such interaction to get a non-equilibrium steady state of certain entropy production. Also, what will happen if we look into the system from a low dimensional phase space? Let's say we have many degrees of freedom, let's say x1, x2 and a different degree of freedom, and we looked into its effect in a low dimensional only in x1 and x2. What will happen to the entropy production rate? And also we want to reinvestigate this energy balance thing with our entropy production based analysis. To do that, we experimentally design a system where we simply trap two colloidal particles in a finite separation d, and to take the system out of equilibrium, we perturb one of the particle with an Ornstein-Uhlenbeck noise such that your dynamical equation of this whole system can be written in terms of x1, x2 and lambda. And with the hydrodynamic interaction, this system is linear. We can write down a force matrix and the diffusion matrix with the cross diagonal terms are there. And this system is multivariate Gaussian. So in each marginal will be Gaussian, and we see from experiment the driven particle, which is here is this sky blue color, the variance of that is higher than which one is the fixed particle, and you can see the non-equilibrium current in difference phase. Then we estimate the entropy production rate using with the interaction and with x1, x2 lambda 3 degree of freedom, and we see the entropy production rate with the interaction is this, and we can take the limit when there is no interaction, we will take epsilon tends to 0. What we get this without the interaction, the entropy production rate in this phase space which is spanned by x1, x2 and lambda is higher than with the interaction. And in experiment we varied this theta. Theta is just basically the strength of the external, theta is in terms of the external noise, and from the experimental data we used this short time inference based key to estimate the entropy production rate, which is just based on this uncertainty relation, which by doing the proper optimization we can get the exact entropy production rate from the data as well, from numerical and experimental data. So we see so these lines are analytical and the points are experiment and the open points are numerics. We see for a particular strength of the noise, we see when the interaction strength is lower, we get the higher entropy production, and if the particles are close by when the interaction is higher, we get a lower entropy production rate. And it can be understood in terms of this: when the particles are close by, if the second particle is not there, the first particle with the drive is the current in that space is higher than the particle close by, because the second particle is actually affecting the motion of the first one in presence of hydrodynamic here. Okay, so and also we see by just tuning this interaction, by just placing the particle in different space, we can get a state of different entropy production rate. Okay, and in this case, in general, it is known that if the interaction is enhanced, generally entropy production is higher, but here the hydrodynamic is kind of giving it's a destructive effect. And then we try to understand what will happen if we just look into the coarse grain phase space. Let's say in general experiment is very difficult to get the actual active degree of freedom in my case lambda. So let's say I only measure x1 and x2. So what we can do, we can properly coarse grain the previous fine grain system, and we can get a reduced drift matrix, and then if we use this to calculate the entropy production rate from data and analytics, we get a completely different trend in presence with the hydrodynamic interaction. we see so these lines, of course the entropy production rate without the lambda is less because we are in a coarse grain space, but the dependence with the hydrodynamic interaction is reversed. Okay, so why it is happening? Because in x1 x2 space, if we coarse grain the lambda, as I show in the probability distribution function, the variance of x1 is higher than x2. So we can say that effectively the temperature of the first particle is higher. Now if the second particle is closer to the first one, then only you get a heat flow from one to another, then only the entropy is higher. So that corresponding to higher interaction state give you the higher thing. And if the particles is far apart, the system is less non-equilibrium. So this is the partial entropy production rate actually shows the different rate. To verify it, what we looked at a system called two temperature model, which was designed in this paper, where they had looked at similar system, but they parted one of the particle with a extra white noise. But this is a by construction, it's a coarse grain model because they consider the correlation of the white noise is proportional to delta T, and they construct this model such that the second particle has temperature T and the first particle is at T plus delta T. And if we calculate the entropy production rate in this case, is indeed matches the trend with the coarse grain version of the wave noise driven model. So we can see that with the interaction strength epsilon, we can actually get a different different trend depending on which phase space you are looking at. And actually by just simply playing with the hydrodynamic coupling strength, you can design many different you can get a non-equilibrium state with different entropy production. So then we look into the energetics. So for the wave noise driven model, the energetics are pretty clear. We are perturbing with extra noise, so we know the input power, and it should be exactly equal to the rate of total dissipated heat. Here we estimated the rate of total dissipated heat through medium entropy production rate, because here if we use the Sekimoto's analysis in every degrees of freedom like x1 and x2, the total heat what we will get will not be exactly equal to the W dot. So then we will get this apparent violation of apparent violation of first law. So to get actual heat, we need to go by this medium entropy production rate, which is matches. And then in the coarse grain phase space, if the particle is at two different temperatures, we can use this fact that the total entropy production rate should be Q1 by T plus delta T minus Q2 by KBT, and if the energy balance holds, we can get the actual heat expression as well. So our entropy based approach can identify the heat flow. Here I show the results with the mean Q dot, but we can show it for short time W and Q as well. So with such interaction also the energy balance actually hold, but we need to take this entropy based approach. So as an outlook, and we looked into the effect of hydrodynamic interaction in terms of tunability and trend reversal in different phase space, and we make an attempt to resolve this issue related to this energy balance in terms of entropy based energetics, and we are interested to look into how information flow happens with such interaction. And I would like to acknowledge the other people, Dr. Srikant from Gothenburg, Professor Supriya Krishnamurthy is here, and two of my seniors from my lab who have graduated, Dr. Abhijit and Subed, and my supervisor, Professor Anand Banerjee, and thank my funding agency, and thank you.
I just have a small clarification with the notation that you used when you said there is a steady state distribution and you said X, so I was a bit confused with what steady state distribution are you describing there? Like, I think it was somewhere in the beginning. Yeah, in that steady state.
Here?
Yeah.
Here?
Yeah.
Here, I mean, this X is x1, x2 lambda, and this is the steady state distribution of the whole system in terms of x1, x2 lambda.
Okay, it's a vector, okay.
Yeah, this x is this x,
Okay.
and m is like here m is 3. So that's what.
So I just wanted to comment that it was a little related to the previous talk, because a 3 degrees of freedom at the same temperature, when coarse grained into 2 degrees of freedom, seem to look like a system with 2 different temperatures.
Yes. Yeah.
Yeah, but I don't know how general that is. I mean, could it be related to the linearity? I mean, the systems are all linear, so I don't know. So the whole thing is a linear system,
Yes,
and that's why we can do the coarse graining so easily also.
Yeah.
So I don't know how general that is, but yeah. Any other questions or comments? If not, let's thank Mr. Jeep and all the speakers of today.